In 1942, as German fighters dominated the skies over Europe, an American engineer who had been rejected by the Air Force due to vision problems created the impossible, a fighter that not only equaled the feared Messerschmitts and Focke-Wulfs, but surpassed them in almost every way. German pilots called it the American Beast. The Allies called it their savior. This is the story of Clarence Kelly Johnson and the P-38 Lightning, the twin-engine aircraft that defied all the rules and changed the course of World War II. Clarence Leonard Johnson was born in 1910 in Ishpeming, Michigan, a small mining town in the heart of the state's Upper Peninsula. He was the seventh of 9 children in a family of Swedish immigrants who worked in the iron mines. Life was hard, money was scarce, and his future seemed preordained to work in the mines like his father and older brothers. But Clarence was different. From an early age, he was obsessed with understanding how things worked. He dismantled clocks, built cars from scrap materials, and spent hours watching birds fly. The way birds controlled their flight, adjusting their wings and tails with millimeter precision, fascinated him deeply. He filled notebooks with drawings of imaginary flying machines. At 13, Clarence had a life-changing experience. A traveling aviator arrived in town with a biplane, offering paid flights. Most people saw it as a dangerous novelty, but Clarence saved every penny he could until he had enough for a 15-minute flight. When the plane took off and he saw his town shrinking below, something clicked inside him. He knew exactly what he wanted to do for the rest of his life. The problem was that boys from poor families in mining towns didn't become aeronautical engineers. There was no money for college. There were no connections or opportunities. But Clarence had something more valuable than money: sheer determination and an extraordinary mind for mathematics and physics. At school, he devoured every science book he could find. Teachers noticed his exceptional talent and encouraged him. One of them lent him engineering textbooks, which Clarence read by candlelight after long workdays helping his family. He didn't just read. He memorized equations, solved complex problems mentally, and visualized aerodynamic forces in 3 dimensions. His classmates began calling him Kelly after he got into a fight defending a girl who was being bullied. The nickname stuck, and Clarence went by Kelly Johnson for the rest of his life. The name sounded more American, more confident, more fitting for someone who planned to achieve the impossible. When it came time to decide on college, the Johnson family had no resources, but Kelly had accumulated perfect grades and impressed all his teachers. He earned a partial scholarship to the University of Michigan, supplementing with night jobs in restaurants and auto repair shops. He slept 4 hours a night, studied obsessively, and still found time to build model airplanes that he tested in makeshift wind tunnels. The university professors quickly realized that Kelly was no ordinary student. He saw engineering problems in ways others couldn't. While his classmates were struggling with equations, Kelly was already 3 steps ahead, visualizing entire solutions in his mind. He wasn't just learning aeronautical engineering, he was reinventing it. During his college years, Kelly developed a philosophy that would guide him for the rest of his career. Simplicity is efficiency. The best designs aren't the most complex, but those that achieve maximum performance with minimal complication. It was a revolutionary idea in an era when engineers tended to overcomplicate designs, but Kelly had a problem that threatened to end her dreams before they even began. Kelly Johnson graduated in 1932, in the midst of the Great Depression. The American economy was collapsing. Factories were closing, millions were unemployed, and jobs for newly minted engineers were virtually non-existent. But Kelly had a specific dream: to fly in the United States Army Air Force as a test pilot and engineer. He presented himself for recruitment with confidence, carrying his honors degree and glowing letters of recommendation from professors. The initial physical tests went well. Kelly was in excellent physical shape. The mental aptitude tests were exceptional. He scored at the absolute top. It seemed his dream was about to come true. Then came the eye exam. Kelly had suffered from moderate myopia since childhood, something he had learned to compensate for so well that it rarely affected his daily life. But military standards were uncompromising. Pilots required perfect vision, no exceptions. The military doctor looked at him sympathetically and uttered the words that shattered Kelly. Rejected due to visual impairment. Kelly tried to argue. He could wear glasses. His vision wasn't that bad. He had compensatory abilities. He understood aerodynamics better than any other candidate. None of that mattered. The rules were absolute. He was permanently disqualified from flying in the Air Force. The rejection was devastating. Kelly had built his entire life around that goal. He had sacrificed years, worked himself to exhaustion, overcome immense obstacles, and it was all negated by something completely beyond his control. Many would have given up right then and there, found another career, abandoned aviation. Kelly Johnson did the opposite. If he couldn't fly the planes, then he would create the best planes the world had ever seen. If the Air Force didn't want him as a pilot, he would become so valuable as an engineer that they would beg for his contributions. Rejection didn't destroy him, it transformed him. He landed a job at Lockheed Aircraft Corporation in Burbank, California in 1933. It was a junior position, low-paying, doing basic technical work. But Kelly saw it as his gateway. He worked longer hours than anyone else, volunteered for the most difficult projects, and consistently delivered brilliant solutions to problems that baffled senior engineers. His first major contribution came just months after being hired. Lockheed was developing the Electra, a twin-engine transport aircraft. During wind tunnel testing, the plane exhibited worrying instability under certain conditions. Experienced engineers were perplexed. Kelly, the rookie, studied the problem obsessively in his spare time. He identified the problem as the interaction between the twin tails and the airflow from the engines at specific angles. His solution was elegantly simple: redesign the angle and positioning of the tail surfaces. Senior engineers were skeptical. How could a new graduate see something they couldn't? But testing proved Kelly absolutely correct. That moment established his reputation. Kelly Johnson wasn't just competent. He had an intuitive understanding of aerodynamics that went beyond equations and theory. He could visualize airflow, anticipate complex behaviors, and create solutions that others couldn't imagine. But his greatest test was yet to come. And when it arrived, Kelly would create something that would change aerial warfare forever. In January 1937, the United States Army Air Corps issued a seemingly impossible specification. They wanted a high-altitude interceptor fighter capable of speeds exceeding 360 mph at 20,000 feet. To put this in perspective, the fastest fighters of the time barely exceeded 300 mph at sea level. But there were even more challenging requirements. The plane had to reach 20,000 feet in 6 minutes. It had to have heavy weapons. It had to have extended range. And it had to be stable and controllable in all flight conditions. Aircraft manufacturers across the country looked at those specifications and shook their heads. It was technically impossible with the technology available. Kelly Johnson, now 27, and already recognized as one of Lockheed's most brilliant engineers, saw it differently. He didn't see impossibilities. He saw a fascinating puzzle waiting to be solved. And he had a radical idea that went against all fighter design conventions of the time. Conventional wisdom dictated that fighters should have a single, powerful engine mounted in the front, pulling the plane along. This was how all fighters were built. But Kelly saw the limitations of this approach. A single engine large enough to achieve the required speeds would be extremely heavy. This would require a stronger, heavier airframe to support it. The additional weight would hamper climb performance. It was a vicious cycle. Kelly's solution was counterintuitive: use 2 smaller engines instead of 1 large one, but not mounted in the front. That would create excessive drag. Instead, he would mount them in streamlined nacelles on the wings, each with its own propeller. The central fuselage would be a narrow, streamlined gondola housing the pilot and weapons. A twin tail would connect everything. When Kelly presented his initial sketches to Lockheed management, the reaction was skeptical. A twin-engine fighter? That had never been done before. It would be too heavy. Coordinating two engines would be too complex. What would happen if one engine failed? The objections were numerous. Kelly answered each one methodically. Two smaller engines combined would weigh less than one large engine of equivalent power. The wing-mounted engine configuration freed the central fuselage to be extremely aerodynamic, reducing drag. If one engine failed, the other would provide enough power to return to base safely. The twin tail would provide superior stability and better control. He spent weeks performing complex calculations, mathematically proving that his radical design would not only meet Army specifications, but significantly exceed them. He built models and tested them in wind tunnels, refining every surface and angle. The data didn't lie. Kelly's concept was technically sound. Lockheed decided to take a risk. They gave Kelly permission to develop a full prototype based on his revolutionary design. He had less than a year to turn concept into reality. The pressure was immense. If he failed, it could end his career and potentially Lockheed's. If he succeeded, it would change aviation forever. Kelly assembled a small team of equally brilliant engineers and technicians. They worked 12 to 14-hour shifts, solving unprecedented technical problems. Each day brought new challenges, and Kelly was determined to overcome them all. The first prototype of what would be called the P-38 Lightning began to take shape in Lockheed's Burbank hangar in the summer of 1938. It was unlike anything anyone had ever seen. The central fuselage was sleek and narrow, almost like a torpedo with wings. The engine nacelles resembled perfect aerodynamic pods. The twin tails gave the plane an almost alien appearance. Kelly personally oversaw every aspect of construction. He didn't just draw. He was on the factory floor, working alongside mechanics and technicians. When a component didn't fit perfectly, Kelly was there with tools in hand, adjusting and refining. He understood that great designs weren't just theory on paper. They were 1,000 tiny details executed to perfection. One of the most critical challenges was the cooling system. Two 1,150 horsepower Allison V1710 engines generated immense heat. Installed in the wings, away from the direct airflow from the front, cooling was problematic. Kelly designed an innovative system of radiators mounted in the rear sections of the engine nacelles, cleverly utilizing the airflow to cool both the oil and the coolant. Another challenge was the armament. Kelly had decided to concentrate all the weapons in the forward section of the central fuselage. This meant there was no need for propeller synchronization. The weapons could fire directly ahead without risking hitting their own propellers. Concentrating fire on one point would create massive destructive power. But it required careful structural design to absorb recoil. The cockpit was another innovation. Kelly created a spacious and comfortable cockpit with excellent visibility. He understood that pilots would fly long and exhausting missions. Comfort wasn't a luxury. It was an operational necessity that directly affected performance. The instrument layout was intuitive, the controls ergonomic. Everything was designed from the pilot's perspective. By January 1939, the XP-38 prototype was complete. It was impressive even sitting in the hangar. The silver paint gleamed under the lights. The lines were futuristic and aggressive. There was a palpable sense that this was something special. But the real test would come in the air. The first flight was scheduled for January 27, 1939. Test pilot Ben Kelsey inspected the plane carefully before climbing into the cockpit. Kelly was nervous but confident. He had checked every calculation 1,000 times. Theoretically, everything should work perfectly. But theory and reality didn't always agree. The engines roared to life, a deep, powerful sound. The XP-38 taxied down the runway, accelerated, and surprisingly smoothly lifted off. Kelly watched from the ground, barely breathing. The first few minutes were critical. If there were any fundamental design flaws, they would be revealed now. Kelsey radioed back. The plane flew like a dream. The controls were responsive. Stability was excellent. Speed was increasing rapidly. He took the prototype through a series of maneuvers, turns, climbs, dives. In each test, the P-38 performed magnificently. When Kelsey landed after 45 minutes of flight, he was smiling broadly. "Kelly," he said, "you've created something special." Subsequent tests confirmed it. The P-38 not only met the Army's impossible specifications, it dramatically exceeded them. There was just one problem. War was coming faster than anyone imagined. While the P-38 was undergoing testing in 1939, Europe was descending into war. In September, Germany invaded Poland. France and Great Britain declared war. The German Luftwaffe quickly demonstrated devastating air superiority with its Messerschmitt Bf-109s and coordinated bombers. The Blitzkrieg, lightning war, showed the world that air power had become decisive in modern conflicts. The United States officially remained neutral, but military observers sent alarming reports. Existing American fighters were completely outdated compared to the Germans. The P-40 Warhawk, the best fighter in American production, was inferior to the Bf-109 in virtually every respect. If the United States were drawn into the war, it would be at a serious disadvantage. The Army Air Corps dramatically accelerated the P-38 program. They ordered immediate production of 300 units, even before full testing was completed. It was a calculated risk. If serious problems were discovered, hundreds of planes could be rendered useless. But time was more critical than caution. Kelly and his team worked at a frantic pace, identifying and solving problems as they arose during testing. One of the most serious was compressibility. In high-speed dives, the P-38 encountered strange aerodynamic effects near the speed of sound. The controls became extremely heavy or locked up completely. Pilots reported terrifying experiences losing control in dives. The problem was that the P-38 was simply too fast for the conventional aerodynamics of the time. In high-altitude dives, it reached speeds where the airflow over the wings approached the speed of sound, creating shock waves that drastically altered flight characteristics. It was a phenomenon engineers barely understood in 1940. Kelly tackled the problem with his characteristic approach, meticulous testing and incremental modifications. He redesigned the control surfaces, added special fins to improve high-speed handling, and modified the wing profile. It wasn't a perfect solution. The P-38 would still have limitations in very high-speed dives, but it was manageable with proper pilot training. Another challenge was production logistics. The P-38 was more complex than conventional fighters. It had more parts and more sophisticated systems requiring greater manufacturing precision. Scaling production from a few test units to hundreds per month was a massive industrial engineering challenge. Kelly worked directly with factory managers, streamlining processes wherever possible without compromising performance. In December 1941, when Japan attacked Pearl Harbor and the United States officially entered World War II, only a few P-38s were in operational service. The first combat units were just beginning training. Meanwhile, American pilots were fighting P-40s and other inferior aircraft against the Japanese in the Pacific and the Germans in North Africa. The losses were terrible. Field reports spoke of superiorly maneuverable Japanese Zeros shooting down P-40s with ease. Messerschmitts dominated the skies over the Mediterranean. Commanders desperately clamored for better aircraft. The pressure on Kelly and Lockheed was immense. Soldiers were dying while waiting for the lightning. Kelly pushed production even faster. He worked 18-hour days, solving manufacturing problems, training maintenance crews, and consulting with pilots. He knew that every day of delay meant more lives lost. The P-38 needed to reach the battlefield, and when it did, it needed to be devastatingly. Effective. The first P-38 Lightnings arrived in the European theatre of operations in late 1942. Pilots who saw them for the first time were simultaneously impressed and skeptical. The plane was undeniably beautiful, with its futuristic lines and shiny silver finish. But it was also large for a fighter, bigger than anything they had flown before. Had it sacrificed agility for speed? Training quickly dispelled any doubts. The P-38 was unlike anything American pilots had experienced. With two engines totaling 2,300 horsepower, acceleration was brutal. A top speed of 414 miles per hour at 25,000 feet made it one of the fastest fighters in the world. Its climb rate was exceptional. It could reach 20,000 feet in less than 7 minutes, but it was the combat characteristics that truly impressed. The concentrated armament, 4 50-caliber machine guns and a 20mm cannon, generated devastating firepower. Because all the weapons were located in the central fuselage, there was no dispersion. The projectiles converged on a single, lethal point. A 2-second burst from the P-38 could literally cut an enemy aircraft in half. Range was another crucial advantage. With full fuel tanks, the P-38 could fly over 2,100 miles, more than twice as far as most fighters. This meant it could escort bombers deep into enemy territory, something impossible for single-engine fighters. Bomber pilots would soon learn to love the sight of Lightnings flanking them. The first significant combat came over North Africa in November 1942. Squadrons of P-38s faced Messerschmitt Bf 109s and Focke-Wulf, Freischärnzeites of the Luftwaffe. The German pilots, seasoned veterans with years of combat experience, expected to easily outmaneuver the fledgling Americans. What happened completely surprised them. The P-38s used their advantages of speed and firepower brutally. They attacked from high altitude in high-speed dives, fired devastating bursts, and accelerated away before the Germans could react. If the Germans tried to pursue, the Lightnings simply drove them away. It was a new tactic based on the aircraft's unique capabilities. Reports from the field began to arrive. A P-38 had shot down 3 Bf-109s in a single engagement. Another had destroyed a Junkers Ju-88 bomber with a single burst. The loss ratios were favorable. For every Lightning lost, 2 to 3 German aircraft were shot down. Pilots who were initially skeptical of the unconventional design became fanatical. Believers, the Germans quickly developed a healthy respect for the P-38. Luftwaffe pilots reported that the American twin-tailed plane was a formidable adversary. Some called it the Gabelschwanz Teufel, the fork-tailed demon. There were specific instructions on how to combat it. Never attempt to compete in speed or climb. Avoid head-on engagements and attack only if you have a significant numerical or positional advantage. In the Pacific, the P-38 found even greater success. Against the agile but lightly armed Japanese Zeros, the tactic was similar. Use superior speed and firepower to avoid prolonged maneuvering engagements. Extended range was particularly valuable over the vast distances of the Pacific. Lightnings could escort bombers across hundreds of miles of ocean, but the P-38's true test would come on one of the most audacious and important missions of the war. And Kelly Johnson had no idea that his plane was about to dramatically change history. In April 1943, American intelligence intercepted and deciphered a Japanese message revealing something extraordinary. Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack and supreme commander of the Imperial Japanese Navy, was to conduct an inspection of bases in the South Pacific. The message included his complete itinerary, including exact arrival and departure times. Yamamoto was more than a military officer. He was the strategic genius behind the initial Japanese victories. His death would be a devastating blow to Japanese morale and command capabilities. But there was a critical problem. Yamamoto would be on Bougainville, deep in Japanese-held territory, more than 400 miles from the nearest American base on Guadalcanal. No American fighter had sufficient range to fly the mission, except one. The P-38 Lightning, with auxiliary fuel tanks, could theoretically make the round trip, but it would be a mission at the absolute limit of the plane's range. Any diversion, any prolonged combat, and the pilots would have no fuel to return. The mission was approved at the highest level. President Roosevelt himself personally authorized it. It was designated Operation Vengeance. 16 P-38s from the 339th Fighter Squadron were selected. The plan was to fly extremely low over the ocean to avoid Japanese radar detection, intercept Yamamoto's plane exactly at its scheduled arrival time, shoot it down, and return before Japanese fighters could react. It was incredibly risky. The pilots would have to navigate perfectly across more than 400 miles of ocean, using only compasses and stopwatches. An error of even a few degrees would mean missing the target completely. They would have to time their approach to intercept Yamamoto at just the right moment. And they would have to do all this while flying just 50 feet above the waves to avoid detection. On the morning of April 18, 1943, 16 Lightnings took off from Henderson Field on Guadalcanal. Each carried auxiliary fuel tanks mounted under the wings, giving them the necessary range, but also making them less agile. The pilots flew in absolute radio silence, maintaining close formation just a few meters above the waves. Navigation was the responsibility of Lieutenant Rex Barber, who used meticulous calculations and constant course adjustments. For 2 hours, the P-38s roared across the ocean, salt water spraying from their propellers. Some pilots later reported seeing sharks swimming below them. At exactly 9:35, when the calculations predicted, the pilots spotted 2 Mitsubishi Betty bombers escorted by 6 Zero fighters, exactly as intelligence had predicted. Yamamoto was in one of the Bettys. The auxiliary tanks were jettisoned immediately. 4 P-38s climbed to engage the Zeros. The others dived on the bombers. What followed was a frenetic and brutal dogfight. The Zeros desperately tried to defend the bombers, but the P-38s were faster and the American pilots were determined. Lieutenant Barber positioned himself behind one of the Bettys and opened fire. His 20mm cannon and machine guns ripped through the bomber's fuselage. The Betty, with Yamamoto inside, attempted to escape by flying low over the jungle. Barber pursued relentlessly, firing burst after burst. The bomber began to emit smoke, then burst into flames. It crashed into the jungle and exploded. Admiral Yamamoto died instantly on impact. The P-38's most important mission had been executed with deadly perfection. After Operation Vengeance, the P-38 Lightning solidified its reputation as one of the most lethal fighters of World War II, but it was its daily operations over Europe that truly demonstrated the versatility and capability of Kelly Johnson's design. In the European theater, the P-38 found its primary role as a long-range escort fighter. Formations of B-17 Flying Fortress and B-24 Liberator bombers penetrated deep into Germany, attacking factories, refineries, and infrastructure. These missions were extremely dangerous. Without escort, bombers were slaughtered by German fighters. The Luftwaffe had developed tactics specifically to destroy these heavy bomber formations. The P-38, with its exceptional range, dramatically changed this balance. For the first time, bombers had fighter protection throughout the mission. German pilots who had previously been able to attack bombers with relative impunity now faced aggressive Lightnings, protecting their precious cargo. The statistics told the story. Before the introduction of the P-38 as a long-range escort, the bomber loss rate on deep missions often exceeded 10%, unsustainable in the long run. With Lightning escort, losses dropped to 2 to 3%. Every P-38 in the air meant dozens of bomber crews returning alive. P-38 pilots developed sophisticated tactics specific to their unique characteristics. One was the boom and zoom, diving from high altitude with tremendous speed, firing a devastating burst, and accelerating back down, return to altitude before enemies could react. The P-38's superior speed made this extremely effective. German fighters simply couldn't keep up. Another tactic exploited massed armament. In head-on combat, normally considered extremely risky, the P-38 had a decisive advantage. Its weapons converged perfectly in the center, while German fighters with wing-mounted armament were significantly dispersed. Experienced Lightning pilots could shoot down enemies in head-on passes that would have been suicidal for other aircraft. The European winter of 1943-1944 brought new challenges. Extremely low temperatures at high altitudes caused problems with the Allison engines. Oil froze, radiators cracked, and engines failed. Kelly Johnson, still overseeing modifications and improvements in California, worked frantically on solutions. New heating systems were developed, special cold-resistant fluids were formulated, and operating procedures were adjusted. American aces began to emerge, flying P-38s. Richard Bong, the leading American ace of the war with 40 victories, flew exclusively Lightnings. Thomas Maguire, the second leading ace with 38 victories, was also a P-38 pilot. Both operated in the Pacific, where the Lightning truly shone against the Japanese. In the Pacific, the P-38 was virtually invincible when flown correctly. Its superior speed meant it could choose when to engage and when to retreat. Zeros and other Japanese fighters were more maneuverable at low speeds, but in high-speed combat they were completely outclassed. American pilots learned never to attempt to compete in low-speed maneuvers. Always use speed and energy. The P-38's versatility was remarkable. In addition to fighter and escort roles, it was used as a fighter-bomber, carrying up to 3,200 pounds of bombs. Photographic reconnaissance versions, unarmed but equipped with cameras, penetrated deep into enemy territory, photographing strategic targets. Some variants were adapted as night fighters. Kelly's fundamental design was so solid that it accepted extensive modifications. In June 1944, when Allied forces invaded Normandy on D-Day, P-38s were among the first planes over the beaches. They provided close air cover for the landing troops, attacked German fortifications, and engaged any Luftwaffe fighters brave enough to show up. In the skies over France, the distinctive twin-tail profile became a symbol of liberation. But perhaps the most significant tribute to the P-38 came from its enemies. Captured German pilots consistently ranked the Lightning among the most feared Allied fighters. They respected its speed, firepower, and versatility. One veteran Luftwaffe pilot said during interrogation, "The P-38 was an adversary we never underestimated. It was fast, deadly, and flown by Americans who learned to use its advantages perfectly." Kelly Johnson rarely spoke about his role in creating the Lightning. For him, it was just work, solving technical problems, improving designs, supporting the pilots who risked their lives. But as the war raged on, it became clear that his impossible plane was changing the course of the conflict. By the time the war in Europe drew to a close in 1945, more than 10,000 P-38 Lightnings had been produced. The aircraft had flown in every theater of operation, from the freezing cold of Alaska to the scorching heat of the South Pacific. It had shot down more enemy aircraft than any other American fighter in the Pacific. It had escorted countless bombers home safely. It had saved literally thousands of lives. But for Kelly Johnson, the P-38 was just the beginning. The experience of designing and refining the Lightning under extreme pressure had taught him valuable lessons. He had learned that radical and unconventional designs could succeed if based on sound engineering principles. He had learned the importance of working in small, focused teams without excessive bureaucracy. He had learned that simplicity and efficiency trumped elaborate complexity. In 1943, while the P-38 was proving its worth in combat, Kelly was working on something even more revolutionary. Lockheed had been chosen to develop the first American jet fighter. Kelly led the project, applying the lessons learned from the Lightning. He assembled a small team of exceptional engineers, sequestered them in a separate facility away from corporate bureaucracy, and gave them complete freedom to innovate. The result was the P-80 Shooting Star, developed in just 143 days, an extraordinary record. The aircraft flew days before the end of the war in Europe, arriving too late for significant combat. But it established the United States as a leader in jet aviation technology. And the development method, small team, maximum range, focus on practical results, became the model for future projects. Kelly formalized this approach by creating what became known as Skunk Works, a special division of Lockheed dedicated to advanced and secret projects. The name came from a popular comic strip, but the concept was serious. Skunk Works would operate outside normal corporate structures, with minimal oversight and maximum creative freedom. It was the opposite of how large corporations typically operated. Kelly's operating principles for Skunk Works were simple yet revolutionary. Small teams of exceptional people, direct authority from the project manager over all aspects, minimal documentation and bureaucracy, physical proximity between engineers, manufacturers, and test pilots, rapid iteration based on real-world testing rather than prolonged theoretical analysis. This was essentially how he had developed the P-38, now codified in formal methodology. Over the following decades, Skunk Works, under Kelly's leadership, would produce some of the most iconic and advanced aircraft in history. The U-2, a high-altitude spy plane that flew above 70,000 feet. The SR-71 Blackbird, still the fastest manned aircraft ever built, capable of Mach 3.3, the F-117 Nighthawk, the first operational stealth aircraft. Each pushed the limits of the technologically possible. Kelly received numerous awards and honors. The National Medal of Science, 2 Collier Trophy Awards, the Institute of Aeronautical Sciences Sylvanus Albert Reed Award. He was inducted into the National Aviation Hall of Fame. But when asked about his achievements, Kelly consistently deflected credit to his teams. "I just remove obstacles," he would say. Talented people do the real work, but those who worked with Kelly knew the truth. His genius lay not only in technical design, but in creating environments where innovation flourished. He shielded his teams from corporate politics. He fought for the resources they needed. He made decisions quickly. And always he focused on practical results. Rather than theoretical elegance, the Michigan boy who dreamed of wings had become one of the greatest aeronautical innovators in history. Kelly Johnson retired from Lockheed in 1975 after 42 years transforming aviation. He was 65, an age when most people slow down. But Kelly had lived several lifetimes of achievement. More than 40 aircraft bore his name as principal designer or key contributor. His inventions had flown higher, faster and farther than anyone in the previous generation could have imagined, but Kelly's legacy transcended specific aircraft. He had fundamentally changed how complex engineering projects were approached. The Skunk Works methodology he created became a model studied in business and engineering schools around the world. Large corporations sought to replicate his principles: small teams, autonomy, rapid iteration, and a focus on results. The P-38 Lightning, where it all began, became an icon of aircraft design. Decades after the war, enthusiasts painstakingly restored Lightnings. Flying examples appeared at airshows, their distinctive twin-engine sound still capable of drawing crowds to their feet. Museums proudly displayed P-38s, recognizing their crucial role in the Allied victory. Pilots who had flown Lightnings in combat maintained veterans associations, meeting annually to share memories. Many attributed their lives to the plane, whether its speed allowed them to escape impossible situations, its endurance bringing them home with a destroyed engine, or its firepower saving them in desperate aerial combat. The P-38 wasn't just a machine to them, it was the brother who had fought alongside them. Kelly rarely attended these meetings. He was fundamentally modest, uncomfortable with attention. When he occasionally appeared, pilots surrounded him, wanting to shake hands with the man who had created the plane they loved. He listened to their stories with genuine attention, asking technical questions about performance under specific conditions. Even in retirement, Kelly was an engineer to the core. In later interviews, Kelly reflected on the irony of his career. He had been rejected by the Air Force because of vision problems. That rejection, devastating at the time, had forced him to find another path. Had he been accepted as a pilot, he likely would have had a respectable but unexceptional career. Instead, the rejection pushed him onto a path where his truly extraordinary abilities could flourish. Sometimes, he once said, what seems like our greatest defeat is actually the necessary redirection for our greatest triumph. If I had become a pilot as I planned, I never would have designed the P-38. I never would have created Skunk Works. Thousands of planes would never have been built. It's a lesson in accepting when life changes our plans. Kelly Johnson passed away in 1990 at the age of 80. Obituaries in newspapers around the world celebrated his achievements. Lockheed lowered flags to half-staff. NASA and the Air Force issued statements honoring his contributions. But perhaps the most meaningful tribute came from a veteran P-38 pilot who wrote a simple letter published in an aviation newspaper. Kelly gave us wings when we needed them most. He gave us speed when we were being pursued. He gave us firepower when we were desperate. He brought us home when we thought we would never return. We who flew his planes owe our lives to a man who could never fly with us, but who gave us the sky anyway. Thank you, Kelly. You saved thousands of us. The boy who dreamed of wings had given wings to the world, and those wings had changed history forever. Imagine being ridiculed by your superiors, rejected by industry, and called crazy for an idea that would change the world forever. In 1928, a 21-year-old Royal Air Force cadet named Frank Whittle proposed something that sounded like science fiction, a propellerless engine that could make planes fly faster than anything in the sky. Everyone said it was impossible. He was decades ahead of his time. This is the story of how one man's obsession created the jet engine and completely transformed modern aviation. Stay until the end, because the biggest twist in this story comes in the final chapters. Frank Whittle was born on June 1, 1907, in Coventry, England, the son of a mechanic. Since childhood, he was fascinated by machines and engines. His father, Moses Whittle, owned a small machine shop where young Frank spent hours observing, learning, and tinkering with equipment. That environment shaped his mind to solve complex mechanical problems. World War I was raging when Frank was just 7 years old. He watched with fascination as the planes occasionally flew over his town. These flying machines captured his imagination in a way that would never leave him. To him, airplanes represented the future, freedom, and the limitless possibilities of engineering. At school, Frank wasn't an exceptional student in all subjects, but he excelled in math and science. His teachers noted his uncanny ability to visualize mechanical problems in 3 dimensions and find creative solutions. By the age of 15, he had already decided he wanted to fly and work with airplanes. In 1923, at 16, Frank attempted to join the Royal Air Force as an aviation apprentice. He was rejected twice for not meeting the minimum physical requirements. He was too short, and his build was considered too weak. Most people would have given up. Frank didn't. He spent 6 months doing intensive physical exercises, forcing his body to grow and strengthen. On his 3rd attempt, in January 1923, he was finally accepted. He entered RAF Cranwell, one of England's most prestigious aviation schools, as an apprentice mechanic. There, he would not only learn to repair aircraft, but also have the opportunity to study flight theory, aerodynamics, and aeronautical engineering. During his training at Cranwell, Frank immediately stood out. His instructors were impressed by his ability to understand not only how airplanes worked, but also why they worked that way. He constantly questioned existing designs, always looking for ways to improve efficiency and performance. In 1926, Frank was selected to become an officer cadet, a rare honor for someone from his humble background. This meant he would receive pilot training and formal education in aeronautical engineering. It was exactly the opportunity he had dreamed of. During his training flights, he wasn't just learning to fly. He was studying every aspect of the aircraft's performance. It was during these years of training that Frank became deeply troubled by the limitations of conventional piston engines. Aircraft of the time relied on engines that turned propellers. As aircraft flew faster, the propellers encountered fundamental physical limits. The propeller tips approached the speed of sound, creating turbulence and drastically losing efficiency. Frank began to wonder, what if there were a completely different way to generate thrust? What if it were possible to eliminate the propeller altogether? These questions kept him awake at night, filling notebooks with calculations and drawings. His colleagues thought he was wasting time on impossible fantasies, but Frank had a growing conviction that he had discovered something important. In 1928, at the age of 21, while still a cadet, Frank Whittle wrote a thesis that would change everything. The title was modest, Future Developments in Aircraft Design, but the content was revolutionary. In that document, he proposed for the first time the concept of a jet turbine engine. Whittle's 1928 thesis proposal was elegantly simple in concept, but radically different from anything else before. Instead of using a piston engine to turn a propeller, he proposed using a turbine driven by jets of hot gas to generate direct thrust. The air would be compressed, mixed with fuel, burned, and expelled at high speed from the rear of the engine. The basic principle was Newton's third law. For every action, there is an equal and opposite reaction. If you expelled gas at high speed backward, the engine would push forward. Rockets had used this principle for centuries, but no one had managed to apply it practically to airplanes. Whittle's genius lay in how he proposed to make this work continuously and controllably. Its design included three main components. First, a compressor at the front that would suck in air and compress it. Second, a combustion chamber where the compressed air was mixed with fuel and burned. Third, a turbine that was turned by the hot exhaust gases, which in turn powered the compressor. The gases were then expelled at high speed, generating thrust. What made the idea even more revolutionary was its efficiency at high altitudes. Piston engines lost power dramatically at high altitudes due to the lower air density. Whittle's jet engine, on the other hand, would perform better at higher altitudes where the air was thinner and aerodynamic drag was lower. Airplanes could fly higher and faster than ever imagined. Whittle presented his thesis to his superiors at Cranwell in October 1928. The reaction was mixed. Some instructors found the idea intriguing from a theoretical standpoint. Others were openly skeptical. The problem wasn't necessarily that the physics were wrong, but that practical engineering seemed impossible with the technology of the time. The materials available in 1928 were a serious concern. Temperatures inside a jet combustion chamber would be extremely high, possibly exceeding 1,000 degrees Celsius. Conventional metals would melt or lose structural strength. The turbines would need to rotate at incredibly high speeds, creating enormous mechanical stresses. The necessary precision manufacturing simply didn't exist. Furthermore, no one knew how to design a sufficiently efficient compressor. Axial or centrifugal compressors existed in industrial applications, but not at the speeds and efficiencies required for a viable aviation engine. Each component of Whittle's proposed system presented engineering challenges that seemed insurmountable. The RAF forwarded Whittle's thesis to the Air Ministry for evaluation. In January 1929, the official response arrived. The ministry acknowledged that the idea was theoretically interesting, but concluded that the practical challenges were too great. They saw no viability for development in the near future. In other words, the idea was officially rejected. To make matters worse, the ministry saw no immediate military potential in the proposal. Europe was in a period of relative peace after World War I. Investment in experimental and unproven technology was not a priority. Military budgets were being reduced, not expanded. Projects that did not offer tangible short-term benefits were discarded. Whittle was deeply disappointed but not surprised. He knew his idea was far ahead of its time. However, he also had an unshakable conviction that he was right. The jet engine was the future of aviation, even if no one else could see it yet. The question wasn't if it would happen, but when and who would make it happen. After official rejection in 1929, Whittle continued his career in the RAF as a pilot and instructor. He graduated from Cranwell in 1928 and was commissioned as a pilot officer. Over the next few years, he served in various positions, always distinguishing himself as an exceptional pilot and innovative thinker. But the idea of the jet engine never left him. In 1930, Whittle attempted to patent his invention. He knew that intellectual protection was crucial, even if no one else wanted to develop it at the time. With the help of colleagues, he prepared a detailed patent application describing the principles and components of the jet engine. British patent number 347206 was granted on January 16, 1930. Obtaining the patent was a victory, but also a burden. British patents required annual maintenance fees. For a young officer on a modest salary, these fees represented a significant financial sacrifice. Whittle paid for it out of his own pocket for several years, hoping that he would eventually find support to develop his invention. During this period, he attempted to interest several British aviation companies in his idea. Armstrong Siddeley, a leading engine manufacturer, initially expressed interest in 1929, but later declined. They too felt the technical challenges were too great. Other companies, such as Bristol and Rolls-Royce, did not even respond to his proposals. The industry was comfortable with piston engines and saw no reason to risk unproven technology. Whittle also faced skepticism within the RAF itself. Many senior officers saw him as an impractical idealist, more interested in science fiction fantasies than operational realities. Some colleagues supported him, but most thought he was wasting time and energy on a hopeless project. The phrase "Mad Whittle" began to circulate in some circles. In 1932, Whittle received a momentous opportunity. He was selected to study mechanical engineering at the University of Cambridge. It was a rare honor and a chance to formally develop his technical skills. He enrolled at Peterhouse College in October 1932 and immersed himself in his studies with characteristic intensity. At Cambridge, Whittle had access to top-notch professors and excellent research facilities. He used every opportunity to refine his jet engine calculations and solve theoretical problems. His undergraduate thesis, completed in 1935, included detailed thermodynamic analyses that mathematically proved that the jet engine was not only possible, but would be superior to piston engines in several important metrics. However, even at Cambridge, he faced doubts. Some professors questioned whether the necessary materials could ever be developed. Others pointed out that existing experimental turbines had terrible efficiencies. Whittle argued that with dedicated development, these problems could be solved. But arguments didn't build engines. The financial situation was becoming unsustainable. In 1935, Whittle was unable to pay the annual renewal fee for his patent. With deep regret, he let the patent expire. This meant that his idea was now in the public domain. Anyone or any country could use his concept without compensation. Years later, this forced decision would have significant consequences. Despite all the frustrations, Whittle refused to give up. He was convinced that the jet engine was not only possible, but inevitable. Someone somewhere would eventually build one. He was determined to be that person, no matter how many years it took or how many obstacles he faced. His persistence was extraordinary. In 1935, after completing his studies at Cambridge, Whittle's fortunes finally began to change. He was introduced to two former RAF colleagues, Rolf Dudley Williams and James Tinling, who were fascinated by his idea. Unlike most, they didn't think Whittle was crazy. They thought he was a genius. Dudley Williams and Tinling weren't engineers, but they were entrepreneurs with important connections. They believed the jet engine had enormous commercial potential, even if development was challenging. What Whittle needed wasn't more theoretical studies, but funding to build a real prototype. They were willing to help secure that funding. Through their connections, they were introduced to a financier named Lancelot Law White, who was interested in innovative technologies. White was impressed by Whittle's passion and technical knowledge. After several meetings in January 1936, White agreed to provide initial financial support. It wasn't much money, but it was a start. On January 27, 1936, a company was formally established, Power Jets Limited. The purpose was to develop and eventually commercialize Whittle's jet engine. Whittle held a stake in the company and would serve as chief engineer. Finally, 8 years after his original thesis, he had the resources to attempt to build his own engine. The first challenge was finding an engineering firm capable of manufacturing the components. The British Thomson Houston Company, BTH, in Rugby, agreed to produce the parts under contract. BTH had experience with steam turbines and industrial compressors, so it had at least some relevant expertise. Detailed design work began in March 1936. Designing each component was incredibly complex. The compressor needed to be able to compress air at rates never before achieved in such a compact device. Whittle opted for a dual-flow centrifugal compressor design. Air entered axially and was expelled radially. It was less efficient than an axial compressor, but much simpler to manufacture with the available technology. The combustion chamber presented enormous challenges. Achieving stable and complete combustion at high airflow velocities was extraordinarily difficult. Whittle developed a design with multiple chambers arranged in a ring around a central axis. Each chamber had its own fuel injector and ignition system. The concept was sound, but making it work in practice would be another story. The turbine was perhaps the greatest challenge of all. It needed to extract enough energy from the exhaust gases to power the compressor, while still leaving enough energy to generate thrust. The temperatures would be extreme, and the rotational speeds would be extremely high. Whittle designed a single-stage turbine with specially strengthened blades made from the finest alloys available. Work progressed slowly throughout 1936 and early 1937. Money was constantly tight. Power jets operated on a shoestring budget, and every technical problem consumed precious resources. Whittle often worked nights and weekends, making calculations and refining designs. His health began to suffer due to stress and overwork. In April 1937, the main components were finally ready. The engine was assembled at BTH's Rugby facility. It was a strange and complex device, unlike any engine ever built. Pipes, valves, measuring instruments, and a seemingly endless jumble of metal parts. Whittle looked at his creation with a mixture of pride and apprehension. 9 years after his original thesis, he was about to find out if his idea would actually work. The engine's first test was scheduled for April 12, 1937. Whittle's small team was nervous, but hopeful. They had worked tirelessly for over a year. Now the moment of truth had arrived. The engine sat on a test bench at BTH, connected to numerous instruments to measure temperature, pressure, rotational speed, and thrust. Whittle personally checked every connection and system before authorizing the start. Fuel was added to the tanks. The electrical systems were energized. An external starter motor would be used to initially spin the compressor until combustion became self-sustaining. The crew took up positions behind protective barriers. No one knew exactly what would happen. At 7:45 p.m., Whittle gave the order to start. The starter motor began to turn the shaft. Gradually, the rotational speed increased. At 2,000 RPM, the igniters ignited, and fuel was injected into the combustion chambers. For an agonizing moment, nothing happened. Then, with a surprisingly loud roar, the chambers ignited. The engine roared to life. The hot gases spun the turbine, which fed the compressor, which supplied more air for combustion. The cycle was working. The rotational speed increased rapidly, 3,000 RPM, 4,000, 5,000. The noise was deafening, a high-pitched whistle mixed with a deep roar no one had ever heard before. It was the sound of the future, but then something went wrong. The speed continued to increase uncontrollably, 6,000 RPM, 7,000, 8,000. Whittle yelled to reduce fuel, but the engine wasn't responding to the controls. It was accelerating on its own, fueled by the intensity of the combustion itself. Vibrations increased dramatically. Instruments shook violently. The test rig's frame began to shake. At 13,000 RPM, far beyond the safe design speed, Whittle made the only possible decision: emergency shutdown. He cut off the fuel supply completely. The engine continued to idle, gradually slowing as the crew watched tensely. Finally, after what seemed like minutes but was only seconds, the engine stopped. Absolute silence fell over the test room. Then someone began to laugh nervously. Others joined in. The tension was broken by a mixture of relief and euphoria. Yes, the engine had gone out of control. Yes, it had nearly destroyed itself. But it had worked. For the first time in history, a practical jet engine had operated successfully. Post-test inspection revealed several issues. The fuel control system clearly needed a complete redesign. Some turbine blades showed signs of excessive thermal stress. The bearings had suffered from the extreme speeds, but fundamentally the concept was proven. Compression, combustion, and exhaust worked together to generate power and thrust. Whittle was elated, but exhausted. That test had drained his physical and emotional energy. In the following days, he suffered a partial nervous breakdown due to years of accumulated stress. Doctors ordered him to rest for a few weeks, but his mind wouldn't rest. He was already thinking about the necessary modifications for the next test. News of the test spread quickly through British aviation circles. For the first time, some important figures began to take Whittle seriously. The RAF showed renewed interest. The Air Ministry requested detailed reports. Maybe, just maybe, that crazy young engineer wasn't so crazy after all. After the April 1937 test, Whittle and his small team embarked on months of intensive redesign and refinement. The engine had proven its concept, but it was far from practical for aircraft use. Every system needed to be improved, every component optimized. The work was meticulous and often frustrating. The fuel control system received priority attention. The runaway acceleration of the first test was caused by uncontrolled positive feedback. Higher RPM generated more compression, which allowed more combustion, which generated even more RPM. Whittle designed a sophisticated mechanical governor that would automatically adjust fuel flow based on RPM and temperature. The combustion chambers were also completely redesigned. The goal was to achieve more uniform and complete combustion. Whittle experimented with different injector configurations, airflow patterns, and chamber geometries. Each configuration was tested, measured, and refined. The process was exhaustive but essential. Materials were a constant concern. Temperatures inside the engine exceeded the capabilities of many available alloys. Whittle worked with metallurgists to identify and test new materials. Special nickel alloys and stainless steel were experimented with. Each new material needed to be tested not only for thermal resistance, but also for fatigue and corrosion resistance. Financing remained a chronic problem. Power jets operated with extremely limited resources. Whittle often paid expenses out of his own pocket. The company was constantly on the brink of bankruptcy. surviving through sporadic capital injections from investors who believed in its long-term potential, even if the immediate results were disappointing. By July 1937, the redesigned engine was ready for further testing. The results were significantly improved. The engine achieved stable and controlled operating speeds. Combustion was smoother and more efficient. The control system worked properly. There were still problems: excessive vibrations, uneven heating, suboptimal efficiency, but the progress was undeniable. Throughout 1938, testing continued regularly. Each test revealed new problems and opportunities for improvement. Whittle developed a deep and intuitive understanding of how the engine behaves under different conditions. He could often diagnose problems simply by the sound of the engine or the appearance of the exhaust. The RAF began to pay closer attention. Officials visited the test facilities and were impressed by what they saw. In November 1938, the Air Ministry finally offered a modest contract for further development. It was an important validation, but the amount was still insufficient to significantly accelerate the work. What Whittle and others in England didn't know was that they weren't alone. In Germany, an engineer named Hans von Ohain was working independently on a very similar jet engine. Von Ohain had begun his work in 1935, a few years after Whittle, but had access to much greater resources through the Heinkel Company. An undeclared race was on. In August 1939, the world situation changed dramatically. Germany invaded Poland, starting World War II. Suddenly, advanced military technology wasn't just interesting, it was urgent. The British government began to wake up to the potential of the jet engine. Additional funds were made available. The project's priority increased significantly. Whittle was promoted to squadron leader and given permission to devote himself full-time to engine development. More engineers were assigned to his team. Better facilities were made available. For the first time, he had adequate resources. But now there was also immense pressure. The war depended on technological innovation. With war in full swing in 1940, the development of Whittle's jet engine took on utmost urgency. The Battle of Britain was raging in the skies. British Spitfire and Hurricane fighters engaged German bombers in desperate dogfights. Speed and altitude were critical advantages. A jet engine could change the balance. What Whittle and the British didn't yet fully understand was that the Germans had already flown the world's first jet aircraft. On August 27, 1939, just days before the invasion of Poland, the Heinkel 178 piloted by Erich Warsitz had taken off using Hans von Ohain's engine. It was a historic flight, but one kept secret. Von Ohain's engine, called the HES-3B, had followed similar principles to Whittle's. The similarity was not entirely coincidental. Both were based on fundamental principles of thermodynamics, but von Ohain had developed his ideas independently. He was unaware of Whittle's work until years later. The expiration of Whittle's patent in 1935 meant the idea was in the public domain. By April 1940, Whittle's engine, now designated the W1, was ready for installation in a real aircraft. The Gloucester Aircraft Company was contracted to build an experimental aircraft specifically designed around the jet engine. The plane would be called the Gloucester E-2839. It was a small, simple design, focused on proving that jet flight was feasible. Construction of the E-2839 was accelerated to the maximum. Gloucester engineers worked double shifts. The W1 engine was continually tested and refined during this period. By December 1940, the engine had accumulated over 100 hours of test bench operation, demonstrating increasing reliability. The date of the first flight was approaching. The W1 engine had a thrust of approximately 860 lb-ft, enough to propel the small E-2839 to respectable speeds. It wasn't powerful enough for operational military applications yet, but it would definitively prove the concept. More powerful versions were already being designed, including the W2 with 1,600 lb-ft thrust. By March 1941, the E-2839 was complete and the engine installed. The aircraft was transported to Cranwell Airfield, ironically the same place where Whittle had studied and developed his original idea 13 years earlier. Ground tests began immediately. The engine performed perfectly, but now it needed to prove itself in flight. Taxi tests began in April. Test pilot, squadron leader Peg Sayer, gradually increased speeds as he rolled down the runway. The aircraft responded well to the controls. The engine delivered smooth, consistent power. Small hops were made, lifting the wheels a few meters. Everything seemed ready for the first full flight. The date was set, May 15th, 1941. The weather was cooperating. Clear skies, calm winds. Whittle was present, of course, along with senior RAF officers and representatives from the Air Ministry. The tension was palpable. 13 years of work, frustration, and persistence were reaching a decisive moment. At 7:40 p.m., Sayer received clearance for takeoff. He advanced the throttle gently. The E-2839 began to roll, gaining speed rapidly. The jet's distinctive whistle grew in intensity. At 75 miles per hour, 120 kilometers per hour, Sayer pulled back on the stick. The nose lifted. The wheels left the ground. Britain's first jet aircraft was in the air. The E-2839 climbed smoothly into the afternoon sky. Sayer initially maintained a low altitude, just a few feet above the runway, gaining confidence in the controls. The plane responded well, perhaps even better than expected. The absence of vibration from the piston engine was remarkable. The flight was surprisingly smooth. On the ground, Whittle watched through binoculars, his heart racing. He could hardly believe it was actually happening. His idea, ridiculed for so many years, was literally flying before his eyes. Tears of emotion filled his eyes. 13 years of struggle were worth it in this single moment. Sayer completed a full circuit around the airfield, gradually gaining altitude to approximately 1,000 feet. He tested the controls in different configurations, making gentle left and right turns. The plane handled beautifully. The throttle response was instantaneous, unlike piston engines, which had noticeable lag. After 17 minutes in the air, Sayer lined up for landing. He smoothly reduced power and descended in a controlled approach. The wheels touched the grass with a slight bump. The E-2839 rolled to a stop. Sayer cut the engine and opened the canopy with a huge smile. He had just made aviation history. The ground crew erupted in celebration. Men who had worked for years at that moment embraced each other. Whittle was surrounded by congratulations, but he was in a state of near emotional shock. The relief and joy were overwhelming. He had been proven right. The jet engine worked not just in theory or on a test bench, but in actual flight. Sayer's report was enthusiastic. He described the flight as absolutely satisfactory and noted that the engine delivered smooth, reliable power. The lack of vibration made the flight remarkably comfortable. Throttle response was excellent. The plane reached speeds approaching 600 kilometers per hour on subsequent flights. Impressive for an early prototype. In the following days and weeks, the E-2839 performed numerous additional test flights. Each flight provided valuable data on performance, handling, and reliability. The engine accumulated dozens of flight hours. Minor issues were identified and corrected, but the fundamental design proved sound. News of the success quickly spread to the highest levels of the British government and military. Winston Churchill was personally informed and showed great interest. The strategic importance was obvious. If the United Kingdom could develop operational jet fighters before Germany, it would gain a significant advantage in the air war. In July 1941, the Air Ministry issued a formal specification for an operational jet fighter. Gloucester Aircraft was contracted to develop what would be called the Gloucester Meteor. Whittle and Power Jets would receive contracts to develop production engines. Finally, after years of obscurity, the project had top national priority and adequate resources. However, developing an operational fighter would be far more complex than building an experimental prototype. The Meteor would require 2 engines for reliability and adequate power. The engines would need to be significantly more powerful than the W-1. Weapons, armor, radio systems, and numerous other components would need to be integrated. It would take years. Meanwhile, the Germans were not standing still. Although the British did not know the full details, Germany was rapidly developing its own jet fighter, the Messerschmitt Me 262. With the massive resources of the Nazi war machine, German development was progressing rapidly. The race was far from over. Whittle was promoted to wing commander in recognition of his achievements. He received honors and public recognition for the first time, but he had little time to bask in the glory. The intense work continued. Improved versions of the engine were urgently needed. Every week counted in the race to get jet fighters operational before the enemy. The period from 1941 to 1943 was one of frantic development. The W-2 engine, the more powerful successor to the W-1, underwent numerous iterations. Each version improved thrust, reliability, or efficiency. The W-2B, developed in 1942, produced 1/600 pounds force of thrust, nearly double that of the original engine. It was suitable for use in operational fighters. The transition from experimental prototype to mass production presented immense challenges. Components that worked when carefully manufactured by skilled craftsmen now needed to be mass-produced by less skilled workers. Precise tolerances were critical. Variations of millimeters could destroy efficiency or cause catastrophic failures. The supply chain was complicated. Many components required specialized materials and manufacturing processes. Turbines needed to be cast from special alloys and then machined with extreme precision. Combustion chambers required specialized welding. High-speed bearings were extraordinarily difficult to manufacture to the required quality. Whittle also faced growing political and bureaucratic tensions. The British government wanted to nationalize jet engine development, removing it from the control of the privately owned power jets. Established manufacturers like Rolls-Royce and Rover wanted a stake in production, creating conflicts over intellectual property and technical control. In 1942, Rover assumed responsibility for engine production, but the relationship between Rover and Whittle was strained. Whittle felt that Rover made design changes without fully understanding the implications. Rover felt that Whittle was overly protective and didn't understand the realities of mass production. The situation was detrimental to progress. Fortunately, a solution emerged in 1943. Stanley Hooker, a brilliant Rolls-Royce engineer, persuaded his company to take over production of Rover's jet engines. Rolls-Royce had unparalleled expertise in aviation engines and precision manufacturing. The transition was completed quickly, and Rolls-Royce Welland engines, based on the W-2B, began mass production. Simultaneously, development of the Gloucester Meteor continued. The first prototype flew on March 5, 1943, using experimental engines. Test flights revealed stability and control issues that required significant modifications. But gradually, the Meteor evolved into a capable operational aircraft. In July 1944, almost exactly 3 years after the E-2839's first flight, the first operational Meteors entered service with the RAF. 616. Squadron was equipped with the new jet fighters and began defensive operations against the V-1 flying bombs that terrorized London. It was a historic moment. British jet fighters were finally in combat. However, the Germans had gotten there first. The German Me 262 had first flown in July 1942 and entered operational service in April 1944, 3 months before the Meteor. With a top speed of over 850 kilometers per hour, the Me 262 was significantly faster than any Allied piston engine fighter. It was an unpleasant surprise for the Allies. Fortunately for the Allies, Adolf Hitler had made a crucial strategic error. He insisted that the Me-262 be modified for use as a fast bomber rather than a pure fighter. This delayed its development and limited its effectiveness. Had Me-262s been deployed en masse as fighters from 1943 onwards, they could have significantly changed the course of the air war. The Meteor, although slightly less advanced than the Me-262, was reliable and effective. RAF pilots quickly learned to exploit its advantages. Its superior speed allowed interceptions impossible for conventional fighters. The absence of a propeller improved forward visibility. The flight was smoother and less tiring for the pilots. World War II ended in May 1945 in Europe and August 1945 in the Pacific. Jet fighters had played only a minor role in the conflict, appearing too late to make a decisive impact. But it was absolutely clear that they represented the future of military aviation. The era of the piston engine and propeller was ending. Frank Whittle was promoted to Air Commodore in 1943 and received numerous honors for his contributions. In 1948, he was appointed a Knight Commander of the Order of the British Empire, becoming Sir Frank Whittle. But the honors came with a bittersweet feeling. He received only $10,000 in compensation for his invention, a ridiculously small sum considering the commercial and strategic value of the jet engine. Whittle left the RAF in 1948, physically and emotionally exhausted. Years of intense stress had taken their toll on his health. He suffered from nervous exhaustion and required prolonged rest. He briefly joined BOAC, British Overseas Airways Corporation, as a technical consultant, but soon retired to a quieter life. Meanwhile, the jet engine was transforming commercial aviation. The de Havilland Comet, the world's first commercial jet, entered service in 1952. It could fly higher, faster, and smoother than any previous commercial aircraft. It ushered in the era of mass air transportation, making intercontinental travel affordable and comfortable. The United States, which had lagged behind in jet technology during the war, quickly caught up. American companies licensed British technology and developed their own designs. Within a few years, American manufacturers like General Electric and Pratt & Whitney were producing jet engines that equaled and eventually surpassed British designs. The evolution of jet engines was extraordinarily rapid. By 1950, just 9 years after the E-2839's first flight, jet engines were 10 times more powerful. By 1960, high-bypass turbofans were being developed, offering much greater efficiency. By 1970, supersonic passenger jets like the Concorde were operating. The speed of progress was dizzying. Today, virtually all large military and commercial aircraft use jet engines. The idea that was ridiculed as impossible in 1928 is now the standard technology, enabling billions of people to fly annually. The fundamental principles developed by Whittle remain the basis of all modern jet engines. Frank Whittle lived to see his invention transform the world. In 1976, he emigrated to the United States and accepted a position at the United States Naval Academy. He continued working on advanced engineering projects well into his old age. He died on August 8, 1996, at the age of 89 in Columbia, Maryland. Whittle's story is extraordinary not only for his technical brilliance, but also for his indomitable persistence. He faced rejection after rejection. He was ridiculed as crazy. He worked with minimal resources for years. He watched other countries develop similar technology while he struggled for funding. But he never gave up. Their story teaches us valuable lessons. Truly, revolutionary ideas often face intense skepticism because they challenge fundamental assumptions. Just because something has never been done before doesn't mean it's impossible. Persistence and conviction can eventually overcome all obstacles. When you board a plane today and feel that powerful thrust during takeoff, remember a young 21-year-old cadet in 1928 who imagined a completely new way to fly. Remember the decades of struggle, the sleepless nights, the failed tests and the gradual triumphs. The jet engine changed the world because one engineer refused to accept that his crazy idea was impossible. Frank Whittle didn't just invent the jet engine. He proved that one person with an idea can change the course of history. His legacy lives on in every jet that flies across our skies, connecting continents, uniting people, and making our world smaller and more accessible. This is the story of how one engineer's crazy idea changed aerial combat and aviation forever. End.